Hello, this video is the solutions to the sample problems for exam 1. We're going to start out with some L'Hopital's rules problems, so let's take a look at this. So you see this first one, the limit as x goes to 1 of x cubed minus 10x squared plus 9 over x minus 1. You can plug 1 in there and you'd easily see that it's 0 over 0, which means it satisfies the conditions for L'Hopital's rule. Either 0 over 0 or infinity over infinity. So here's my little star representing I'm doing L'Hopital's rule. And the derivative would be 3x squared minus 20x. The derivative of the bottom would be 1. So then you reinsert the 1, you'll get negative 17 over 1. So that limit will be negative 17. Let's take a look at number 2. And this is the limit as x goes to 0 of cosine of 3x minus 1 over x squared. This one will also be 0 over 0. So let's take the derivative of the numerator. It's going to be negative 3 sine of 3x. Don't forget the 3 from the chain rule, derivative of 3x. And then, of course, the derivative of cosine is negative sine. The bottom is obviously 2x. Now, if you reinsert 0 here, you're going to have 0 over 0 again. So remember the definition of L'Hopital's rule says that, you can repeat L'Hopital's rule to either come up with a value for the limit, or you can clearly determine that it does not exist. So I'm going to take the derivative of, again, and then the derivative of sine is cosine, but we bring out another 3 from the derivative of 3x, which now makes it from negative 3 now to negative 9. And then from 2x, that's derivative will be 2. So if we now insert 0 in there, cosine of 0 is 1, and then you'll get negative 9 halves. All right, let's take a look at number 3. Now this is one of these problems that actually you could go back to Cal 1 and use if you wanted to. It does satisfy L'Hopital's rule because it's infinity over infinity, either plus or minus infinity. But when we did infinity limits back in Cal 1, if your largest power was the same, all you had to do was take a ratio of their coefficients. So actually, L'Hopital's rule does apply here, but it's actually easier if you don't use it and just say negative 18. Oh, excuse me, that's a typo. Negative 18 over negative 8. Let me fix that. Negative 8, which will then be positive 9/4. Okay, so negative 18 over negative 8. And then I can get rid of the negative here. Positive 9/4. But you could use L'Hopital's rule twice if you wanted to. However, you really would want to use this approach. Let's say if it was x to the 10th over x to the 10th. It would be quite cumbersome to take 10 derivatives, but you would get a large number that would reduce to the same answer. Okie doke, let's see what we got here. Theta approaches 0 of 3 minus 3 cos 0 over sine of cos theta, obviously plugging 0 in there, sine of 4 theta. So when you plug 0 in there, we get 3 minus 3 on top. Sine of 0 is 0, so it's definitely 0 over 0. So here comes L'Hopital's rule. The derivative of negative 3 cosine would be positive 3 sine of theta. And chain rule on the bottom, sine of 4 theta will be 4 cos of 4 theta. Now you insert the 0. You'll get 0 on top, 4 on bottom, and that will equal 0. There we go. Oh, number 5. Here we go. limit as theta goes to 0 of sine of theta to the 7th over theta. All right, so we have definitely 0 over 0. So I'm going to apply L'Hopital's rule. The derivative of sine of theta to the 7th would be cosine of theta to the 7th times the derivative of theta to the 7th, which will be 7 theta to the 6th. And then the derivative of theta on bottom, respect to theta, would just be 1. And this is a typo here I didn't see. But anyway, the answer, yeah, that should be a 1 there. The answer is still 0, though. But obviously that's just a 1 here, because when you plug in the theta on top, 0 for theta, for the 7 theta to the 6th, you have 0. So 0 over 1 makes that 0. All right, so yeah, so it's still 0. That's the correct answer. Just miscopied that 1. Nothing happened. The 1 was still 1. So now we're getting into the ones where they multiply, where they're infinity times 0. And the idea on these problems is that you have to rewrite them in fractional form to be able to apply L'Hopital's rule. And the one thing you need to keep in mind is if there's natural log in the problem, don't drop the natural log, drops whatever's with it. It might be possible, but I've never encountered a problem to where dropping the natural log would be the better way to do it. Maybe there's one out there somewhere, but it's safer to go with the fact you don't do it. And I've certainly never given one on an exam or anything to where you would do that. So this one, because sometimes it's tricky with the trig, whether you drop the trig, whether you drop the other part of it, that doesn't have a hard and fast rule. What I usually like to tell students is if you drop one of them and the problem starts getting worse and worse, then you can always go back and drop the other term. If it starts really turning into a big mess. But these, when you have this x times the trig function of some number over x, you always drop the x. But keep in mind, when you drop the x, you're not just putting x on bottom. You've got to put 1 over x. You have to put the reciprocal. Because dividing by 1 over x is the same as multiplying by x. So we're dropping x to the bottom, but it becomes 1 over x on the bottom. So now I have sine of 10 over x, and then 1 over x on the bottom. Now, the derivative of sine of 10 over x will be cos of 10 over x times the derivative of 10 over x, which I'm not going to actually take that derivative when I show you the next step, but it would be okay if you took the derivative right here. There's going to be a relationship. There's one like this in my notes too, similar idea. Same thing on the bottom, I just wrote it as 1 over x prime. Now I come over here, because you can, when you have the derivative, you can pull a constant out and it's still correct. So it's correct for me to say that the derivative of 10 over x is the same thing as 10 times the derivative of 1 over x. So if you now think about this as 10 times the derivative of 1 over x, the derivatives plural of 1 over x would cancel, and you would just be left with that 10 right there on top. But like I said, if you took those derivatives, you'd get negative 10 over x squared, and you'd get negative 1 over x squared here. The x squares would cancel. You'd have negative 10 over negative 1, and you'd still end up with 10. But I thought that was a little quicker way to do it, but it's okay if you don't do it that way. But anyway, as long as we get to this part right here, where we have the limit of theta, x goes to infinity, of 10 cosine of 10 over x. So you put in infinity. 10 over infinity is essentially going to 0. Cosine of 0 is 1, so you have 10 times 1, and that limit will be 10. Number 7. Sine of 7x over 3x. That's 0 over 0, so we can take L'Hopital's rule. It's going to be 7 cosine of 7x because of the chain rule. 3 on bottom. Put in 0. Cosine of 0 will be 1. And then we have 7 thirds. So that one wasn't too bad. Just 1 L'Hopital's rule and plug it 0 back in there. Now here's another one with an x multiplied by a trig function, like we did 2 problems ago. But this one, it's better to drop the trig function. In fact, you'll see it's real easy. And you might get it to work the other way, but this is just so much easier. Like I said, if things are going bad, you can start over and do it again. But multiplying by cosecant is the exact same thing as dividing by sine, because sine is 1 over cosecant. So I'll leave the 4x on top, take cosecant on top and make it sine on bottom, 0 over 0. Take the derivative, it'll be 4, and the bottom will be cosine of x. Put in 0, cosine of 0 is 1, so we just have 4 over 1 equals 4. All right, so yeah, the trig, there's no steadfast rule on whether the trig function drops or whatever's with it drops. Only natural log has that rule. Now here's the ones that get a little more interesting as far as these, can take some steps here to work these out. Because this is where you have to do the logarithm thing to bring that exponent down. We're getting to the problems where you're either going to have 0 to the 0, infinity raised to the 0, or 1 to the infinity. It's one of those 3 forms. Now you don't have to label or identify. I mean, I'm certainly on an exam, it's going to be one of those forms. You don't have to check. So the first thing you want to do is give this limit some sort of variable name. I just tend to use y for consistency, but if you want to use something else, that's just as long as it's not x. So we take ln of both sides. And when you take the ln, that brings the exponent down. So it's the limit of sine of x times natural log of x. Now, we don't drop the ln, so that you have to get it in fractional form. But these will be consistent in the sense that you're always going to have an ln here. So whatever's with it's what's going to go to the denominator every time. So now we have the limit as x goes to 0 from the plus side. That generally won't matter for the plus and minus that much here. It's not going to be anything, the one-sided limit's not going to affect how you do the problem. Sometimes it's there for, in this case, because the natural log can't be, you can't have 0 or negative numbers, so we'd have to approach it from only the positive side. So it's more of a conceptual idea here than actual numerically solving the problem. So we're going to use, here's the star from L'Hopital's rule. So there's the star. So ln of x will be 1 over x. The derivative of cosecant x will be negative cosecant cotangent. Now what I did here is rewrote these in terms of sine and cosine. So cosecant is 1 over sine. Cosine is 1 over sine. Cosine over sine, excuse me. So it would leave a sine squared. It'd be a cosine over a sine squared. So that flips the sine squared up and over to the top. So you'd have a sine squared here, and then x is on the bottom next to that cosine. Now, theoretically, that's 0 times 0, and we could use L'Hopital's rule again. But this, actually, this can be verified with L'Hopital's rule, but there was an important limit we learned in Cal 1, and that's going to help us right here to make this problem a lot shorter and quicker if you catch this. Whenever the limit is x approaches 0, and you have either sine of x over x, and it could even be sine of 5x over 5x, that would work too, or x on top, sine x on bottom, that limit's always going to be 1. Now, one thing let me mention real quick here about limits that's not the same as derivatives. Like, for example, the derivative of a product of 2 functions is not the product of the individual derivatives. F times g is not f prime g prime. Remember, we have something called the product rule for the derivatives of 2 functions. Limits are different. The limit of a product is the product of the limits. So you can do what I'm doing right here, and you can break it up into 2 pieces. That is okay with limits. Now, if you catch this, it'll be so much easier. But like I said, you could probably do it without it. It wouldn't be that bad, I guess, but it's just quicker. You got to be careful with the chain rule when you take this derivative, and that's a product rule down there, so it's much more pleasant if you don't do that. So I took away one of the signs, so sine of x over x, as x goes to 0, not just any number, 0. That becomes 1. So now you have sine of x over cos. You just plug 0 right in there. You get 0 on top, 1 on bottom. Now you can say it's 0 for sure. You can never say 0 whenever it's 0 over 0. Now it's 0, but remember, for these kind of problems with the exponent, the answer's not 0, because what we just found to be 0 was the natural log of that limit, not the limit itself. So the last step in these exponential problems is you always take e raised to whatever you have right here. So the actual answer is not 0, it's e raised to the 0, which equals 1. So there's always that e to the power, the very last step. So let's take a look at this one. So the limit as x approaches infinity of 1 plus 2 over x cubed raised to the x. And that's basically 1 to the infinity, because that'll be 0 right here. So we're going to do the same thing. We're going to log it. That's going to bring the x down, and then times the log of what's in the parentheses right here. So once again, we don't drop the natural log. We drop the x on bottom to become 1 over x. Now we can do L'Hopital's rule. The derivative of natural log is the derivative of what's on the inside over what's on the inside. So the derivative of 2 over x cubed, I don't need to use a quotient rule here, that'd be too much trouble. It's 2x to the negative 3. So when you take that derivative, it would be negative 6 x to the negative 4. So the derivative of then 2x to the negative 3 will be negative 6x to the negative 4, so it's negative 6 over x to the 4th. And then there's the denominator right here. And the derivative of 1 over x would be just x to the negative 1, so it'll be negative 1, negative x to the negative 2, which is negative 1 over x squared. So now I drop that denominator down to the very bottom here. And there's several ways you can kind of go about this on the algebra part. So notice that's a L'Hopital step, but and it's still 0 over 0, so it's got to be manipulated. Now this time though, there's no other L'Hopital steps that's required. The rest of this is just algebra. So I dropped this down. I distributed the negative 1 over x squared. Multiplied through and got this relationship, and then I decided let's get this out of a complex fraction form by multiplying by the largest power of those three x's, which is x to the 5th. In other words, that will get it into a single fraction to where it's no longer a complex fraction. And we have, so I did x to the 5th over x to the 5th times every term. That gives you this. Negative 6x over negative x cubed minus 2. Now, I will mention that technically, you could do L'Hopital's rule here because it's infinity over infinity. But let me mention, now, one of the earlier problems, remember I told you, when it goes to infinity, if you have the same power on the top and bottom, you take their coefficients. Well, another similar rule to that that applies with infinity, is that if you have a larger power on bottom than top, it's going to go to 0 automatically. Now, if I had done L'Hopital's rule, I would have then gotten negative 6 on top, negative 3x squared on bottom, then it would have been negative 6 over infinity, so it still would have been 0. So it's okay if you don't do L'Hopital's rule, because we can be absolutely sure that it was going to be 0 even without it. But you don't want to take too many liberties like that. But there are, it's the infinity situations that has these special cases. And then we got 0, but once again, 0 would not be the answer because that's the natural log of the limit. So the answer is actually y equals e to the 0, which is 1. Number 11, we have x raised to the 1 over 4x minus 4. Now I kind of combined a couple steps here. So when you log it, ln in front, comes down to be 1 over x minus 4. Now, unlike, if it's just x when it comes down, x comes down, you got to make it 1 over x on the bottom. But notice this is already a fraction. So when this comes down, the bottom of that fraction will already be in the bottom of this fraction. So it's just ln of x. This comes down, makes 4x minus 4 on bottom. Then once we do that one, this one doesn't have too many steps here. 1 L'Hopital's rule. ln of x will have a derivative of 1 over x. 4x minus 4 will be 4, so you plug in 1, you'll get 1 on top. 4 on bottom, you'll get 1/4. And then the answer then, of course, will be e raised to the 1/4. All right. So that takes care of L'Hopital's rule. Let's move on to some questions on the shell method for finding the volumes. The shell method is the one that uses like the tubes, if you want to call them, or circular. They're also known as cylindrical shells. I've seen people refer to it as those. Cylindrical shells, instead of using discs and volt washers, and you're summing up all these shells. Now the one thing that, and later on you'll see the problems on the disc and washer method. One thing that makes this kind of confusing is that which axis you use for which method. For example, using the shell method, if you're revolving it around the y-axis, it will be variable x. And if it's x-axis, it'll be variable y. And that's going to be not just the opposite for the disc and washer method. If it's around the y-axis, you're going to be using variable y in your integration. If it's x-axis, you'll be using variable x. So you might think we have to solve this in terms of y. We do not. So essentially, this is if I drew the little representative rectangle, they call it, this isn't going to look very good because I'm not using a stylus. It's just freehand here, but it would look like that. No, excuse me. No, it wouldn't. All right, forget I did that. It will look like this. It's vertical. Almost got myself confused between the disc shell and the disc. Okay, vertical, like that. And then the p of x will be that distance from the x-axis, which is x. And h of x is the vertical distance. So let's say if you're between two curves or something, it would be the upper curve minus the lower curve. All right. But this one, there's just that curve and the x-axis, so h of x will be 2 plus x squared over 25. And so all we do is the formula has 2 pi, whereas the disc and washer just has 1 pi. And we're going from 0 to 5, x-axis limits of integration, and we multiply x times 2 plus x squared plus 25. So once you get these set up, they're not too hard to do. It's just, now I'm showing you how to do them manually, but I don't mind if you do these, obviously in a graphing type calculator. So, but here, if you distribute it out, you'll get this. Then take the antiderivative of 2x will be x squared. X cubed over 25 will be x to the 4th over 100. 0 to 5. So doing it that way, and that fraction all reduces to 125 over 2 pi. So if you enter this in the calculator, like I did right there, and then made it into a fraction, 125 over 2 times pi. Okay. So we're going about the x-axis instead of the y. So our rectangle would look something like that. Yeah, the representative rectangle is always parallel for the shell method to the axis of revolution. So it's going to be, the height of that's going to be y. Now here's where you have to be careful. The values for x, it's the difference between two functions. It's the right minus the left, outer minus the inner. So say that height would be y for the shell, but then the length would be either 2 and then minus the inside curve. So it's 2 minus, it'd be easy just to think it's the square root of y, 4 minus y squared. That would be true if it was this inner empty region, that would be true. Now, if this was done by the disc washer method, you definitely have a washer here because it's got a gap in there. But this one, there's no concerns about washers. But you do have to set at certain times subtract the function. So, and of course, p of y, that height's just y. 2 minus the square root of 4 minus y. So the volume is going to be 2 pi. We're going to 0 to 2, and I'm mentioning that I know they're both 0 to 2, so I'm just clarifying it does mean 0 to 2, on the y-axis. So, okay, so yeah, we didn't want you to think it was this 2 down here on the x. Just coincidence, they're both 2s, but it's important for you to know which one, in case, when they aren't the same. All right, so I'll kind of go through the quick part of this, the integration. But the key is the setup. Now this one I split the integrals up. I thought it'd be a little easier to do. So I just kind of took this 2y, dealt with it by itself, because I knew that was going to be easy. That ends up just yielding 8 pi. And the next one is y times the square root of 4 minus y squared, minus 1/2. Not this one's hard, it's just obviously not as easy as that first one. So I just did a basic u substitution, no big deal. 4 minus y squared, negative 2y. And then you got a negative 1/2 for the du. So you have to adjust for that. U of 2 is 0, u of 0 is 4. So we have minus 2 pi, because the 2 pi, along with the y, distributes to both terms here. So it's 0 to 2 still. Negative 1/2 from the du. And then the u to the 1/2, when you integrate this now, it'll be u to the 1/2, which will be 2/3 u to the 3/2. And then 0 on top and 0 on bottom. So essentially these 2's cancel, the negatives cancel. You have 2 pi over 3, and then 0 to the 3/2 is 0, 4 to the 3/2 is 8, so that's going to be subtraction. So it's 24 pi over 3 minus 16 pi over 3, which will equal 8 pi over 3. Okay. Now we're back to a y-axis problem. I guess I didn't. Let's see. Let's see what we have. I went ahead and graphed this one on the calculator. Just take a look at it. Pretty easy to do. There's the 2 graphs. So the blue one will be 6x squared, the parabola, and 6 times square root of x. Now this is going to be in terms of variable x, going around the y-axis. And your p of x, no, there's your representative rectangle right here. And then it's the horizontal distance of x from the axis. Don't worry about that curve. That curve will come into play, but the p of x and p of y are just the distance from whatever axis you're revolving it from. So just give you an example. I believe I mentioned this in the lecture video for this section, but just an example. Let's say if you were revolving it, I don't generally do that on exams and stuff, so that's why I don't worry about it, but I do mention it, and it's sort of good to know. But so let's say if I was revolving it around x equals negative 1, you would actually, so the distance would not just be x, it would be x minus a minus 1, meaning you're x plus 1 away from the axis of revolution. So, but using the x and y axis just means it's always going to be x. Now the h of x is where you've got to consider the 2 functions. So it's upper minus lower. If we were revolving around the x-axis, it'd be y minus right minus left. Upper minus lower. Now, of course, if you get these backwards, it just means you'll get the negative of the right answer. But still, might as well do it right the first time. So the upper is the square root of x, the red graph, a 6 square root of x, and then 6x squared is the lower. So here's the setup for that one. And the limits of integration are the x-axis, 0 to 1, of course 2 pi, your p of xx times the difference in these two. So not a hard integral. Of course, like I said, you can do it in the calculator, but it's not that hard. Distribute, so that becomes 6x to the 3/2 minus 6x cubed. So these are just power rule problems, no substitutions or anything. Antiderivative, so of x to the 3/2 will be 2/5 x to the 5/2. So times 6 makes that 12/5 x to the 5/2. And then x cubed will be x4 over 4. So 6 over 4 reduces to 3 over 2. And there's the x to the 4th from 0 to 1. Those are good numbers to plug in because they're easy. And so it's going to give you just 12/5 minus 3/2. Common denominator of 10. So it's 2 pi times 24 over 10 minus 15 over 10, which is 9 over 10. And then the 2 on top will reduce with a 10 to make it 5. So it's 9 pi over 5, or 9 over 5 times pi, however you want to say it. All right. Now here's one back to going around the x-axis. So its x-axis needs to be variable y. And I drew that little what they call a representative rectangle. And it's a horizontal rectangle. Let's see. And the vertical distance would be y. Okay. And there are the graphs, the two lines. I didn't put the window there, but I think you can pretty much tell which is which. Obviously, the straight line has to be the one y equals x minus 6. And the other one's y equals square root of x. But then they need to be solved for x in terms of y, which isn't too difficult. If y equals the square root of x, x would equal y squared. And then if x equals y plus 6, y equals x minus 6 would lead to x equals y plus 6. So it's going to be right minus left. So the line is on the right, it'll go first, y plus 6, and the curve is on the left, it will go second. So that'll be y plus 6 minus y squared. And then times your y, because that's your p of y, your height. And then put the y in front. So this was just a basic antiderivative. Just distribute the y through here. You get y squared plus 6y minus y cubed. Take the antiderivative. And that'll be 1/3 y cubed plus 3y squared minus 1/4 y to the 4th. And then we plug in 3, we plug in 0, and then we get, so you plug in 3 into 1/3 y cubed. Remember, 3 cubed is 27, not 9, but 1/3 of that will be 9. And then 3y squared, 3 times 9 will be 27. And then 1/4 y to the 4th, 3 to the 4th will be 81. So you got 81 over 4. So all I did here was take 36 and rewrite it as common denominator 144 over 4. So I get 63 over 4, and then that 2 with the 2 pi will reduce that to 63 over 2 times pi. And then there you see the result in the calculator. So that completes problem number 15.